Isaac Newton. 1. The Mathematician. He was born in a small farm at Woolsthorpe, in the county of Lincoln, on December 25, 1642, Old Style, the year in which Galileo died. Cultural, like economic leadership, was passing from the south to the north. At birth he was so small that, his mother later told him, he might have been put into a quart mug, and so weak that no one thought he would live beyond a few days. As his father had died some months earlier, the boy was brought up by his mother and an uncle. At 12 he was sent to the public school at Grantham. He did not do well there. He was reported as idle and inattentive, neglecting prescribed studies for subjects that appealed to him, and giving much time to mechanical contrivances like sundials, water wheels, and homemade clocks. After 2 years at Grantham he was taken from school to help his mother on the farm, but again he skimped his duties to read books and do mathematical problems. Another uncle, recognizing his ability, sent him back to school and arranged for Newton's admission to Trinity College, Cambridge, in 1661 as a subsizar, a student who earned his expenses by various services. He took his degree 4 years later and was soon thereafter elected a Fellow of the college. He dealt chiefly with mathematics, optics, astronomy, and astrology. In this last study he maintained interest till late in his life. In 1669 his mathematics teacher, Isaac Barrow, resigned, and on Barrow's recommendation of him as an unparalleled genius, Newton was appointed to succeed him. He held this chair at Trinity for 34 years. He was not a successful teacher. So few went to hear him, his secretary recalled, and fewer that understood him, that oft-times he did in a manner for want of hearers read to the walls. On some occasions he had no auditors at all, and returned sadly to his room. There he built a laboratory, the only one then to be found in Cambridge. He made many experiments, mainly in alchemy, the transmuting of metals being his chief design, but also he was interested in the elixir of life and the philosopher's stone. He continued his alchemist studies from 1661 to 1692, and even while writing the Principia he left unpublished manuscripts on alchemy totaling 100,000 words or more, wholly devoid of value. Boyle and other members of the Royal Society were feverishly engaged in the same quest for manufacturing gold. Newton's aim was not clearly commercial. He never showed any eagerness for material gains. Probably he was seeking some law or process by which the elements could be interpreted as transmutable variations of one basic substance. We cannot be sure that he was wrong. Outside his rooms at Cambridge he had a small garden. There he took short walks, soon interrupted by some idea which he hurried to his desk to record. He sat little, but rather walked about his room so much that, said his secretary, you might have thought him among the Aristotelian sect of peripatetics. He ate sparingly, often skipped a meal, forgot that he had missed it, and grudged the time he had to give to eating and sleeping. He rarely went to dine in the hall, and then, if he had not been reminded, would go very carelessly, with shoes down at the heels, stockings untied, and his head scarcely combed. Many stories were told, and many were invented, about his absent-mindedness. On awakening from sleep, we are assured, he might sit on his bed for hours undressed, engrossed in thought. When he had visitors, he would sometimes disappear into another room, jot down ideas, and quite forget his company. During those 35 years at Cambridge, he was a monk of science. He drew up rules of philosophizing, that is, of scientific method and research. He rejected the rules which Descartes in his Discours had set up as a priori principles from which all major truths were to be derived by deduction. When Newton said, I do not invent hypotheses, he meant that he offered no theories as to anything beyond observation of phenomena. So he would hazard no guess as to the nature of gravitation, but would only describe its behavior and formulate its laws. He did not pretend to avoid hypotheses as cues to experiments. On the contrary, his laboratory was devoted to testing 1,000 ideas and possibilities, and his record was littered with hypotheses tried and rejected. Nor did he repudiate deduction. He merely insisted that it should start from facts and lead to principles. His method was to conceive possible solutions of a problem, work out their mathematical implications, and test these by computation and experiment. The whole burden of natural philosophy, he wrote, seems to consist in this: from the phenomena of motions to investigate the forces of nature, and then from these forces to demonstrate the other phenomena. He was a compound of mathematics and imagination, and no one can understand him who does not possess both. Nevertheless, we proceed. His fame has two foci, calculus and gravitation. He began his work on the calculus in 1665 by finding the tangent and radius of curvature at any point on a curve. He called his method not calculus, but fluxions, and gave for this term an explanation upon which we cannot improve. Lines are described and thereby generated not by the apposition of parts, but by the continued motion of points. Superficies, or planes, by the motion of lines, solids by the motion of superficies, angles by the rotation of the sides, portions of time by continual flux, and so in other quantities. Therefore, considering that quantities, which increase in equal times and by increasing are generated, became greater or less according to the greater or less velocity with which they increase or are generated, I sought a method of determining quantities from the velocities of the motions or increments in which they are generated, and calling these velocities of the motions or increments fluxions, and the generated quantities fluents, I fell by degrees upon the method of fluxions in the years 1665 and 1666. Newton described his method in a letter to Barrow in 1669 and referred to it in a letter to John Collins in 1672. He probably used the method in reaching some of the results in his Principia of 1687, but his exposition there, probably for the convenience of his readers, followed accepted geometrical formulas. He contributed a statement of his fluxions procedure, but not over his own name, to Wallace's Algebra in 1693. Not till 1704, in an appendix to his Optics, did he publish the account just quoted. It was characteristic of Newton to delay publication of his theories. Perhaps he wished first to resolve the difficulties suggested by them, so he waited till 1676 to announce his binomial theorem, though he had probably formulated it in 1665. These deferments embroiled the mathematicians of Europe in a disgraceful controversy that for a generation disrupted the international of science. For between Newton's communication of his fluxions to his friends in 1669 and the publishing of the new method in 1704, Leibniz developed a rival system at Mainz and Paris. In 1671 he sent to the Académie des Sciences a paper containing the germ of the differential calculus. On a visit to London, January to March 1673, Leibniz met Oldenburg. He had already corresponded with him and Boyle. Newton's friends later believed, historians now doubt, that Leibniz on this trip received some suggestion of Newton's fluxions. In June 1676, at the request of Oldenburg and Collins, Newton wrote a letter for transmission to Leibniz, explaining his method of analysis. In August, Leibniz replied to Oldenburg, including some examples of his own work in calculus. And in June 1677, in a further letter to Oldenburg, he described his form of differential calculus and his system of notation, which differed from Newton's. In the Acta Eruditorum for October 1684, he again expounded the differential calculus, and in 1686 he published his system of integral calculus. In the first edition of the Principia in 1687, Newton apparently accepted Leibniz's independent discovery of calculus. In letters which went between me and that most excellent geometer, G.W. Leibniz, 10 years ago, when I signified that I was in the knowledge of a method of determining maxima and minima, of drawing tangents and the like, that most distinguished man wrote back that he had also fallen upon a method of the same kind, and communicated his method, which hardly differed from mine except in his forms of words and symbols. This gentlemanly acknowledgment should have contracepted controversy. But in 1699, a Swiss mathematician, in a communication to the Royal Society, suggested that Leibniz had borrowed his calculus from Newton. In 1705, Leibniz, in an anonymous review of Newton's Optics, implied that Newton's fluxions were an adaptation of the Leibnizian calculus. In 1712, the Royal Society appointed a committee to examine the documents involved. Before the year was out, the Society published a report, Commercium Epistolicum, asserting the priority of Newton, but leaving open the question of Leibniz's originality. In a letter of April 9, 1716, to an Italian priest in London, Leibniz protested that Newton's scholium had settled the question. Leibniz died November 14, 1716. Soon afterward, Newton denied that the scholium allowed him, Leibniz, the invention of the calculus differentialis, independently of my own. In the third edition of the Principia in 1726, the scholium was omitted. The dispute was hardly worthy of philosophers, since either claimant might have bowed to Fermat's priority. 2. The physicist. Mathematics, however wonderful, was only a tool for calculating quantities. It did not profess to understand or describe reality. When Newton turned from the tool to the ultimate quest, he addressed himself first to the mystery of light. His first lectures at Cambridge were on light, color, and vision. Characteristically, he did not publish his Optics till 35 years later, in 1704. He had no itch to print. In 1666, he bought a prism at Sturbridge Fair and began optical experiments. From 1668 onward, he made a succession of telescopes. Hoping to avoid some defects persisting in the refracting telescope, he made with his own hands a reflecting telescope, on theorems set forth by Mersenne in 1639 and James Gregory in 1662, and presented it to the Royal Society at its request in 1671. On January 11, 1672, he was elected to membership in the Society. Even before making telescopes, he had reached in 1666 one of his basic discoveries, that white light, or sunlight, is not simple or homogeneous, but is a compound of red, orange, yellow, green, blue, indigo, and violet. When he passed a small ray of sunlight through a transparent prism, he found that the apparently monochrome light divided into all these colors of the rainbow, that each component color emerged from the prism at its own specific angle or degree or refraction, and that the colors arranged themselves in a row of bands forming a continuous spectrum, with red at one end and violet at the other. Later investigators showed that various substances, when made luminous by burning, gave different spectra. By comparing these spectra with one made by a given star, it became possible to analyze in some degree the star's chemical constituents. Still more delicate observations of a star's spectrum indicated its approximate rate of motion toward or from the Earth, and from these calculations the distance of the star was theoretically deduced. Newton's revelation of the composition of light and its refraction in the spectrum has therefore had almost cosmic consequences in astronomy. Hardly foreseeing these results, but feeling, as he wrote to Oldenburg, that he had made the oddest if not the most considerable detection which hath hitherto been made in the operations of nature, Newton sent to the Royal Society early in 1672 a paper entitled New Theory about Light and Colors. It was read to the members on February 8th and aroused a controversy that crossed the Channel to the continent. Hooke had described in his Micrographia in 1664 an experiment similar to Newton's with the prism. He had not deduced from it a successful theory of color, but he felt slighted by Newton's ignoring his priority, and he joined with other members of the Society in criticizing Newton's conclusions. The dispute lingered on for 3 years. "I am so persecuted," wrote the thin-skinned Newton, "with discussions arising out of my theory of light that I blamed my own imprudence for parting with so substantial a blessing as my quiet to run after a shadow." For a time he was inclined to resolutely bid adieu to philosophy eternally, except what I do for my own satisfaction. Another point of controversy with Hooke concerned the medium through which light is transmitted. Hooke had adopted Huygens's theory that light traveled on the waves of an ether. Newton argued that such a theory could not explain why light traveled in straight lines. He proposed instead a corpuscular theory. Light is due to the emission by a luminous body of innumerable tiny particles traveling in straight lines through empty space with a speed of 190,000 miles per second. He rejected ether as a medium of light, but later accepted it as a medium of gravitational force. Newton gathered his discussions of light into the Optics of 1704. Significantly, it was written in English. The Principia was in Latin, and was addressed to readers of quick wit and understanding not yet versed in optics. At the end of the book he listed 31 queries for further consideration. Query 1 suggested prophetically, "Do not bodies act upon light at a distance, and by their action bend its rays? And is not this action strongest at the least distance?" Compare this with page 88 of Einstein's Relativity, published in 1900. And query 30, "Why may not nature change bodies into light, and light into bodies?" 3. The genealogy of gravitation. The year 1666 was germinal for Newton. It saw the beginning of his work in optics, but also, he later recalled, "In May I had entrance into the inverse method of fluxions. and in the same year I began to think of gravity extending to the orbit of the moon, having thereby compared the force requisite to keep the moon in her orbit with the force of gravity at the surface of the earth, and found them to answer pretty nearly. In those years I was in the prime of my age. In 1666 the plague reached Cambridge, and for safety's sake Newton returned to his native Woolsthorpe. At this point we come upon a pretty story, wrote Voltaire in his Philosophie de Newton in 1738. One day in the year 1666, Newton then retired to the country, seeing some fruit fall from a tree, as I was told by his niece, Madame Conduit, fell into a profound meditation upon the cause which draws all bodies in a line which, if prolonged, would pass very nearly through the center of the earth. This is the oldest known mention of the apple story. It does not appear in Newton's early biographers, nor in his own account of how he came to the idea of universal gravitation. It is now generally regarded as a legend. More likely is another story in Voltaire, that when a stranger asked Newton how he had discovered the laws of gravitation, he replied, "By thinking of them without ceasing." It is fairly clear that by 1666 Newton had calculated the force of attraction holding the planets in their orbits as varying inversely with the square of their distance from the sun. But he could not as yet reconcile the theory with his mathematical reckonings. He laid it aside and published nothing about it for the next 18 years. The idea of interstellar gravitation was by no means original with Newton. Some 15th century astronomers thought that the heavens exert a force upon the earth like that of the magnet upon iron, and that since the earth is equally attracted from every direction, it remains suspended in the sum total of all these forces. Gilbert's De Magnete, from 1600, had set many minds thinking about the magnetic influences surrounding every body, and he himself had written, in a work that would be published in 1651, 48 years after his death, "The force which emanates from the moon reaches to the earth, and in like manner the magnetic virtue of the earth pervades the region of the moon. Both correspond and conspire by the joint action of both, according to a proportion and conformity of motions, but the earth has more effect in consequence of its superior mass." Ismailis Bouillard, in his Astronomia Philolaica, from 1645, had held that the mutual attraction of the planets varies inversely as the square of the distance between them. Alfonso Borelli, in Theories of the Medicean Planets in 1666, held that every planet and satellite revolves round some principal globe of the universe as a fountain of virtue, or force, which so draws and holds them that they cannot by any means be separated from it, but are compelled to follow it wherever it goes, in constant and continuous revolutions. And he explained the orbits of these planets and satellites as the resultant of the centrifugal force of their revolution, as we find in a wheel or a stone whirled in a sling, countered by the centripetal attraction of their sun. Kepler considered gravity inherent in all celestial bodies, and for a while he reckoned its force as varying inversely with the square of the intervening distance. This would have clearly anticipated Newton, but later he rejected this formula and supposed the attraction to be diminished in direct proportion as the distance increased. These approaches to a gravitational theory were deflected by Descartes' hypothesis of vortices forming in a primeval mass and then determining the action and orbit of each part. Many of the alert inquirers in the Royal Society puzzled over the mathematics of gravitation. In 1674, Hooke, in An Attempt to Prove the Annual Motion of the Earth, anticipated by 11 years Newton's announcement of the gravitation theory. I shall explain a system of the world, differing in many particulars from any yet known, answering in all things to the common rules of mechanical motions. This depends upon three suppositions. First, that all celestial bodies whatsoever have an attractive or gravitating power towards their centers, whereby they attract not only their own parts and keep them from flying from them, but that they do also attract all other celestial bodies that are within the sphere of their activity. The second suggestion is this, that all bodies whatsoever that are put into direct and simple motion will so continue to move forward in a straight line till they are by some other effectual powers deflected. The third supposition is that these attractive powers are so much the more powerful in operating by how much nearer the body wrought upon is to their own centers. Hooke did not in this treatise reckon the attraction as varying inversely with the square of the distance, but if we may believe Aubrey, he communicated this principle to Newton, who had already arrived at it independently. In January 1684, Hooke propounded the formula of inverse squares to Wren and Halley, who themselves had already accepted it. They pointed out to Hooke that what was needed was no mere supposition, but a mathematical demonstration that the principle of gravitation would explain the paths of the planets. Wren offered to Hooke and Halley a reward of 40 shillings, or $100, if either would bring him within 2 months a mathematical proof of gravitation. So far as we know, none came. Sometime in August 1684, Halley went to Cambridge and asked Newton what would be the orbit of a planet if its attraction by the sun varied inversely as the square of the distance between them. Newton replied, an ellipse. As Kepler had concluded from his mathematical study of Tycho Brahe's observations that the planetary orbits are elliptical, astronomy seemed now confirmed by mathematics and vice versa. Newton added that he had worked out the calculations in detail in 1679, but had laid them aside, partly because they did not fully accord with the then current estimates of the Earth's diameter and the distance of the Earth from the Moon. More probably because he was not sure that he could treat the Sun, the planets, and the Moon as single points in measuring their attractive force. But in 1671, Picard announced his new measurements of the Earth's radius and a degree of longitude, which last he calculated at 69.1 English statute miles. And in 1672, Picard's mission to Cayenne enabled him to estimate the distance of the Sun from the Earth as 87 million miles. The present figure is 92 million. These new estimates harmonized well with Newton's mathematics of gravitation, and further calculations in 1685 convinced him that a sphere attracts bodies as though all its mass were gathered at its center. Now he felt more confidence in his hypothesis. He compared the rate of fall in a stone dropped to the Earth with the rate at which the Moon would fall toward the Earth if the gravitational pull of the Earth upon the Moon diminished with the square of the distance between them. He found that his results agreed with the latest astronomical data. He concluded that the force making the stone fall and the force drawing the Moon toward the Earth, despite the Moon's centrifugal impetus, were one and the same. His achievement lay in applying this conclusion to all bodies in space, in conceiving all the heavenly bodies as bound in a mesh of gravitational influences, and in showing how his mathematical and mechanical calculations tallied with the observations of the astronomers, and especially with Kepler's planetary laws. Newton worked out his calculations anew and communicated them to Halley in November 1684. Recognizing their importance, Halley urged him to submit them to the Royal Society. He complied by sending the Society a treatise, Propositiones de Motu, in February 1685, which summarized his views on motion and gravitation. In March 1686, he began a fuller exposition, and on April 28, 1686, he presented to the Society, in manuscript, Book 1, De Motu Corporum, of Philosophiae Naturalis Principia Mathematica. Hooke at once pointed out that he had anticipated Newton in 1674. Newton answered in a letter to Halley that Hooke had taken the idea of inverse squares from Borelli and Bouillard. The dispute waxed to mutual irritation. Halley acted as peacemaker, and Newton soothed Hooke by inserting into his manuscript, under Proposition 4, a scholium in which he credited our friends Wren, Hooke, and Halley as having already inferred the law of inverse squares. But the dispute so irked him that when he announced to Halley on June 20th, 1687, that Book 2 was ready, he added, "The third I now design to suppress. Philosophy is such an impertinently litigious lady that a man had as good be engaged in lawsuits as have to do with her." Halley persuaded him to continue, and in September 1687 the entire work was published under the imprint of the Royal Society and its current president, Samuel Pepys. The Society being short of funds, Halley paid for the publication entirely out of his own pocket, though he was not a man of means. So at last, after 20 years of preparation, appeared the most important book of 17th-century science, rivaled in the magnitude of its effect upon the mind of literate Europe only by the De Revolutionibus Orbium Coelestium, from 1543, of Copernicus, and The Origin of Species, in 1859, of Darwin. These 3 books are the basic events in the history of modern Europe. 4. The Principia. The preface explained the title. Since the ancients, as we are told by Pappus, made great account of the science of mechanics in the investigation of natural things, and the moderns, laying aside substantial forms of the scholastics and occult qualities, have endeavored to subject the phenomena of nature to the laws of mathematics, I have in this treatise cultivated mathematics as far as it regards natural philosophy. Therefore, we offer this work as mathematical principles of philosophy, for all the difficulty of philosophy seems to consist in this: from the phenomena of motions to investigate the forces of nature, and then from these forces to demonstrate the other phenomena. The viewpoint is to be strictly mechanical. I wish we could derive the rest of the phenomena of nature by the same kind of reasoning from mechanical principles, for I am induced by many reasons to suspect that they may all depend upon certain forces by which the particles of bodies, by some causes hitherto unknown, are either mutually impelled towards each other and cohere in regular figures, or are repelled and recede from each other, which forces being unknown, philosophers have hitherto attempted the search of nature in vain. But I hope the principles here laid down will afford some light either to that or some truer method of philosophy. After laying down some definitions and axioms, Newton formulated 3 laws of motion. 1. Every body continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. 2. The change of motion is proportional to the motive force impressed and is made in the direction of the straight line in which that force is impressed. 3. To every action there is always opposed an equal reaction. Armed with these laws and the rule of inverse squares, Newton proceeded to formulate the principle of gravitation. Its current form, that every particle of matter attracts every other particle with a force varying directly as the product of their masses and inversely as the square of the distance between them, is nowhere found in these words in the Principia. But Newton expressed the idea in the general scholium that closes Book 2. Gravity operates according to the quantity of the solid matter which they, the sun and the planets, contain, and propagates its virtue on all sides, decreasing always as the inverse square of the distances. He applied this principle and his laws of motion to the planetary orbits and found that his mathematical calculations harmonized with the elliptical orbits deduced by Kepler. He argued that the planets are deflected from rectilinear motions and are kept in their orbits by a force tending toward the sun and varying inversely as the square of their distances from the center of the sun. On similar principles, he explained the attraction of Jupiter upon its satellites and of the Earth upon the moon. He showed that Descartes' theory of vortices as the first form of the cosmos could not be reconciled with Kepler's laws. He calculated the mass of each planet and figured the density of the Earth as between 5 and 6 times that of water. The current figure is 5.5. He accounted mathematically for the flattening of the Earth at the poles, and ascribed the bulge of the Earth at the equator to the gravitational attraction of the sun. He worked out the mathematics of tides as due to the combined pull of the sun and the moon upon the seas, and by similar lunisolar action he explained the precession of the equinoctial points. He reduced the trajectories of comets to regular orbits, and so confirmed Halley's prediction. By attributing gravitational attraction to all planets and stars, he pictured a universe mechanically far more complex than had been supposed. For now every planet or star was viewed as influenced by every other. But into this complex multitude of heavenly bodies Newton placed law. The most distant star was subject to the same mechanics and mathematics as the smallest particles on the earth. Never had man's vision of law ventured so far or so boldly into space. The first edition of the Principia was soon sold out, but no second edition appeared till 1713. Copies became so scarce and hard to secure that one scientist transcribed the whole work with his own hand. It was recognized as an intellectual enterprise of the highest order, but some notes of criticism soured the praise. France, clinging to Descartes' vortices, rejected the Newtonian system until Voltaire gave it a worshipful exposition in 1738. Cassini and Fontenelle objected that gravitation was just one more occult force or quality. Newton propounded certain relationships among the heavenly bodies, but he had not revealed the nature of gravitation, which remained as mysterious as God. Leibniz argued that unless Newton could show the mechanism by which gravitation could act through apparently empty space upon objects millions of miles away, gravitation could not be accepted as anything more than a word. Even in England, the new theory was not readily received. Voltaire claimed that 40 years after its first publication, hardly 20 scientists could be found favorable to it. Whereas in France, critics complained that the theory was insufficiently mechanical as compared with Descartes' primeval whirlpools, in England, the objections were predominantly religious. George Berkeley, in Principles of Human Knowledge in 1710, regretted that Newton had thought of space, time, and motion as absolute, apparently eternal, and existing independently of divine support. Mechanism so pervaded the Newtonian system that there seemed no place in it for God. When Newton, after characteristic delays, agreed to prepare a second edition, he tried to appease his critics. He assured Leibniz and the French that he did not assume a force acting at a distance through empty space. He believed in an intervening medium of transmission, though he would not attempt to describe it, and he frankly confessed that he did not know the nature of gravitation. It was in this connection that he wrote in the second edition the oft-misunderstood words, non fingo hypotheses. Gravity, he added, must be caused by an agent acting constantly according to certain laws. But whether this agent be material or immaterial, I have left to the consideration of my readers. To further meet religious objections, he appended to the second edition a general scholium on the role of God in his system. He restricted his mechanistic explanations to the physical world. Even in that world he saw evidences of divine design. The great machine required some initial source of its motion, which must be God. Moreover, there were in the solar system certain irregularities of behavior which God periodically corrected as they arose. To make room for such miraculous interpositions, Newton surrendered the principle of the conservation of energy. The world machine, he now supposed, lost energy in time and would run down if God did not intervene to restore its force. This most beautiful system of the sun, planets, and comets, he concluded, could only proceed from the counsel and dominion of an intelligent and powerful being. Finally, he moved toward a philosophy that could be interpreted in either a vitalistic or a mechanistic sense. And now we might add something concerning a certain most subtle spirit which pervades and hides in all gross bodies, by the force and action of which spirit the particles of bodies attract one another at near distances and cohere if contiguous, and electric bodies operate to greater distances, as well repelling as attracting the neighboring corpuscles. And light is emitted, reflected, refracted, inflected, and heats bodies. And all sensation is excited, and the members of animal bodies move at the command of the will, namely by the vibrations of this spirit, mutually propagated along the solid filaments of the nerves, from the outward organs of sense to the brain, and from the brain into the muscles. But these are things that cannot be explained in a few words, nor are we furnished with that sufficiency of experiments which is required to an accurate determination and demonstration of the laws by which this electric and elastic spirit operates. What was his actual religious faith? His professorship at Cambridge required allegiance to the established church, and he attended Anglican services regularly. But, says his secretary, as for his private prayers, I can say nothing of them. I am apt to believe his intense studies deprived him of the better part. Yet he studied the Bible as zealously as he studied the universe. An archbishop complimented him. "You know more divinity than all of us put together." And Locke said of his knowledge of the Scriptures, "I know few his equals." He left theological writings greater in bulk than all his scientific works. His studies led him to semi-Arian conclusions, much like those of Milton, that Christ, though the Son of God, was not equal in time or power with God the Father. For the rest, Newton was or became quite orthodox. He seems to have taken every word of the Bible as the word of God, and to have accepted the books of Daniel and Revelation as literal truth. The greatest scientist of his age was a mystic who lovingly copied out large passages from Jacob Boehme, who asked Locke to discuss with him the meaning of the white horse in the Apocalypse. He encouraged his friend John Craig to write Theologiae Christianae Principia Mathematica in 1699, which sought to prove mathematically the date of Christ's second coming and the ratio between the highest attainable earthly happiness and the believer's rewarding bliss in paradise. He wrote a commentary on the Apocalypse and argued that the Antichrist therein predicted was the Pope of Rome. Newton's mind was a mixture of Galileo's mechanics and Kepler's laws with Burma's theology. We shall not soon see his like again. 5. Evening. He was in another sense an anomalous mixture, a man apparently absorbed in mathematical and mystical theory, and yet possessed of practical ability and common sense. In 1687 he was chosen by the University of Cambridge to go with others and protest to James II the king's attempt to have the university admit a Benedictine monk to a degree without taking the usual oaths impossible to a Catholic. The mission failed to dissuade the king, but the university must have approved Newton's conduct of it, for he was chosen member for Cambridge in the Parliament of 1689. He served till the dissolution in 1690 and was re-elected in 1701, but he took no memorable part in politics. His career was interrupted in 1692 by 2 years of physical and mental illness. He addressed to Pepys and Locke letters complaining of sleeplessness and melancholia, expressing fears of persecution, and mourning that he had lost the former consistency of his mind. On September 16, 1693, he wrote to Locke, "Sir, being of opinion that you endeavored to embroil me with women and by other means, I was so much affected that when one told me you were sickly and would not live, I answered 'twere better if you were dead. I desire you to forgive me for this uncharitableness, for I am now satisfied that what you have done is just, and I beg your pardon for having hard thoughts of you for it, and for representing that you struck at the root of morality in a principle you laid down in your book of ideas, and designed to pursue in another book, and that I took you for a hobbist. I beg your pardon also for saying or thinking that there was a design to sell me an office or to embroil me. I am your most humble and unfortunate servant, Isaac Newton." Pepys, in a letter of September 26, 1693, mentioned a discomposure in head or mind, evidenced by a message he had received from Newton. Huygens left at his death in 1695 a manuscript in which he noted, under the date of May 29, 1694, that Mr. Colin, a Scotchman, informed me that 18 months ago the illustrious geometer Isaac Newton had become insane, but had so far recovered his health that he began to understand the Principia. Huygens sent the report to Leibniz in a letter of June 8, 1694. "The good Mr. Newton has had an attack of phrenitis which lasted 18 months, and of which they say his friends have cured him by means of remedies and keeping him shut up. Some have supposed that this nervous breakdown led Newton from science to the apocalypse, but we cannot say. It was said that he never again concentrated after the old fashion or did any fresh work. Yet he solved almost at once in 1696 a mathematical problem proposed by Johann Bernoulli to the acutest mathematicians in the world, and he did likewise with a problem set by Leibniz in 1716. His answer to Bernoulli was sent anonymously through the Royal Society, but Bernoulli at once guessed the author to be Newton, recognizing, he said, tanquam ex ungue leonum, the lion from his toenail. In 1700 he discovered the theory of the sextant. He let it remain unknown except by a letter to Halley, and it had to be reinvented in 1730, and he seems to have filled creditably the difficult positions to which he was presently appointed by the state. Locke, Pepys, and other friends had for some time negotiated to secure for Newton a governmental position that would get him away from the confinement of his room and laboratory at Cambridge. In 1695 they persuaded Lord Halifax to offer him the post of Warden of the Mint. The appointment was no sinecure and no act of charity. The government wished to use Newton's knowledge of chemistry and metallurgy in minting a new coinage. In 1695 he moved to London, where he lived with his niece, Catherine Barton, the mistress of Halifax. Voltaire felt that the charm of this niece led Halifax, as Chancellor of the Exchequer, to make Newton Master of the Mint in 1699. But this bit of gossip hardly explains why Newton continued to hold that office through his remaining 28 years, and to the general satisfaction. His old age should have been happy. He was honored as the greatest of living scientists. Not till our own time did any man of science enjoy such wide acclaim. He was elected President of the Royal Society in 1703, and annually thereafter till his death. In 1705 he was knighted by Queen Anne. When he rode in his carriage through the London streets, people gazed with awe upon his pink face, majestic and benevolent under a mass of white hair. And they could not always see that he had expanded out of proportion to his modest height. He enjoyed a good salary, £1,200 a year, and invested his savings so wisely that he left £32,000 when he died, though he had been generous in gifts and charity. He surmounted successfully the South Sea Company fiasco. However, he was moody, sometimes irritable, suspicious, secretive, always timid but proud. He loved privacy and did not make friends readily. In 1700 he proposed to a rich widow. Nothing came of it, and he never married. High-strung and morbidly sensitive, he bore criticism painfully, resented it sharply, and fought back stoutly in controversy. He was conscious of his own work and ability, but he lived modestly until his salary and his savings enabled him to have 6 servants and enjoy a high place in London society. In his 79th year he began to repay his debt to nature. Diseases that respect no genius afflicted him, stone in the bladder and urinary incontinence. At the age of 83 he suffered from gout, and at 84 from hemorrhoids. On March 19, 1727, the pains from the stone were so severe that he lost consciousness. He never regained it, but died the next day in his 85th year. He was buried in Westminster Abbey after a funeral led by statesmen, nobles, and philosophers, in a pall borne by dukes and earls. Poets swathed him in elegies, and Pope composed a famous epitaph. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. Voltaire, even in old age, was moved when he told how, in his English exile, he had seen a mathematician buried with the honors of a king. Newton's fame grew to almost absurd heights. Leibniz judged his rival's contributions to mathematics to be equal in value to all previous work in that science. Hume considered Newton the greatest and rarest genius that ever rose for the adornment and instruction of the species, and Voltaire modestly agreed. Lagrange called the Principia the greatest production of the human mind, and Laplace assured it for all time a preeminence above all other productions of the human intellect. Newton, he added, was the most fortunate of men, for there is only one universe and one ultimate principle in it, and Newton discovered that principle. Such judgments are precarious, for truth, even in science, wilts like a flower. If we rank the greatness of a man by the least subjective test, the spread and duration of his influence, Newton can be compared only with the founders of world religions and pivotal philosophies. For a time, his influence upon English mathematics was harmful, for his fluxions and their notation proved less convenient than the calculus and notation with which Leibniz prevailed on the continent. For a century, his corpuscular theory of light seems to have impeded the progress of optics, though some students now find much help in Newton's view. In mechanics, his work has proved endlessly creative. All that has been accomplished in mechanics since his day, wrote Ernst Mach, has been a deductive, formal, and mathematical development on the basis of Newton's laws. Theologians at first feared the influence of the Principia on religion, but Bentley's Boyle lectures in 1692, encouraged by Newton, turned the new world view to the support of faith by stressing the apparent unity, order, and grandeur of the universe as evidences of the wisdom, power, and majesty of God. However, the same Newtonian system was accepted by the deists as strengthening their replacement of the Christian theology with a simple acceptance of one God, or even their identification of God with nature and her laws. Probably the final influence of Newton on religion was injurious. Despite his protests and his million words of theological writings, freethinkers supposed that he had conceived a self-subsistent world and had brought deity into it as a comforting afterthought. In France especially, Newton's cosmology, though presented deistically by Voltaire, encouraged the mechanistic atheism of many philosophes. Between the decline of the Cartesian cosmogony in France, circa 1740, and the rise of relativity theories and quantum mechanics in the 20th century, Newton's system of the world met no serious challenge, and seemed to be verified by every advance or discovery in physics or astronomy. So far as an outsider can understand such arcana, the principal dissents of contemporary physicists from Newton's mechanics are: 1. Newton took space and distance, time and motion as absolute, that is, not varying in quantity according to anything outside themselves. Einstein considered them relative, varying with the position and motion of the observer in space and time. 2. Newton's first law of motion apparently assumed that a body might continue in a state of rest or of uniform motion in a straight line. But rest is always relative, like the rest of a traveler in a speeding plane. All things move, and never in a straight line, for every line of motion or action is deflected by surrounding bodies, as Newton realized. 3. Newton thought of mass as a constant, Some contemporary physicists think of it as varying with the relative velocity of observer and object. 4. Force is now looked upon as a convenient but not necessary concept in science, which aims to content itself with describing sequences, relations, and results. We do not and need not, we are told, know what it is that passes from a moving object to an object that it strikes. We need only record the sequences and assume, never with absolute certainty, that these will be in the future what they have appeared to be in the past. Gravitation, in this view, is not a force, but a system of relationships among events in space and time. It is a consolation to learn that these and other emendations of Newton's mechanics are of importance only in fields, such as electromagnetic phenomena, where particles seem to move with a speed approaching the velocity of light. Elsewhere, the divergence between the old physics and the new may be safely ignored. Philosophers, cured of certainty by history, may still retain a humble skepticism about contemporary ideas, including their own. They will sense a fluent relativity in relativity formulas, and they will remind all delvers in atoms and stars of Newton's own final estimate of his epical achievement. I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting himself in now and then finding a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lay all undiscovered before me.